Welcome back, everybody, from your breaks. Now, for our last talk, we have our very own Ankur Satle. Ankur is an architect working on telecom products at EXFO. He has extensively worked on high-performance telecom products, network monitoring, OSS, PSS monolith, and distributed systems in his 19 plus years of experience. He's currently exploring some new technology to build a smart data platform for a lot of telecom services and network monitoring. He holds a BTech in electronics and telecom and a postgraduate diploma in software technology. He loves learning languages, natural languages to be more exact, and also enjoys outdoor activities, drawing, and talking about cosmology with students and children. He also loves playing football and watching thrillers and mystery movies, and he's constantly learning something or another, you may find. So, presenting his talk on how C++ eliminated memory issues, here is Ankur himself.
Thank you very much, Anushree. Thanks for the words. Very kind, very kind. All right, I'll just share my screen. Hello, everybody. How C++ eliminated memory issues. If you think of C and C++ languages, the first thing, if you ask anybody about the top kind of issues and errors they face and the biggest impact they have because of, if you ask them because of what kind of issues they have the biggest impact, definitely memory issues have been ruling the roost there for quite a long time now. C started in the 70s, and then C++ took over, and they have been going for a very long. C++ is more than 40 years old now, but memory issues had been a problem. And my claim is we don't have that today. And I'll show you why I say that, and we look at how we may not have these memory issues, which have been a part of our lives, and we can really do without them. Okay, so I just checked on Google, what are the 10 most common C++ dev mistakes? And I won't ask you to read them, but these are the ones where, according to a 2015 article, memory issues were 3 out of those 10. And there were indirect memory issues caused by some of the other problems. For example, if you forget declaring a destructor virtual on number 2 there, you would leak some resources which you may hold in the child classes. So 6 out of 10 is definitely something that should be a big priority for the community and anybody to address. If you look at the common vulnerabilities, do you see my ribbon? Zoom ribbon?
No.
No, you don't? Okay. It's coming in the way for me, by the way.
You can just go on the top, hide meeting controls. Option.
Hide.
On the
Yeah,
right-hand side, click that more button, something like that.
More, hide, floating meeting controls. Thank you very much. So I come back to this slide. This is just yesterday, last night, I took this screenshot of 2022, this year's vulnerabilities. Okay, and security vulnerabilities, which we see, there have already been around 39,000. And these are the top 25. This website maintains the top 25 of them. 6 out of these 25 are because of memory issues. As you see, out of bounds write, out of bounds read, use after free, null pointer dereferencing, improper restriction of operations within the bounds of the memory, and uncontrolled resource consumption, which is memory leaks, right? Uncontrolled consumption, just keep on consuming. Last year, 40% of the points. So if you see there's a score column there, which is the point of, I guess it indicates the seriousness of the issue. 40% of the points were attributed to memory issues. Okay, it's the picture is very gloomy. And what options do we have to counter these? Of course, very special, use Rust. Well, let's hear Sean Parent. This is from his talk. from a few days ago, released on YouTube a few days ago, from CPP Now this May. And I expect it to play. Okay. It was just a few seconds of his line in the 7th minute of this talk. He says something about this code, which he wrote in 30 years ago, actually. And I think it was in Apple, and they still contact Sean Parent for this code. And what he says at the end of it, he's discussing about how he's every now and then he has to pay attention to something he wrote at that time. And he says, may your code be used for 30 years. Okay. If you want a shelf life of 30 years, if you want to build a code today and keep using it forever, if you want to not keep on rebuilding the same product and the same features so that your competitor takes over you, you cannot just keep on rewriting in new languages, etc.
Hopefully, after 30 years, this will die down. So, may all your code be used for 30 years.
I love that if my code is used for 30 years. Okay. Meanwhile, at ISO CPP, at the end of May, sometime in June, June first week, there was this C++ developer survey. And there they had a question, one of the questions. Which of these do you find frustrating about C++ development? And drum roll again, a bigger one this time. Here you see, this is these are all the various options that they gave, and people rated the respondents rated items as major pain point, minor pain point, or not a significant issue for me. And if you see this, these are the memory issues which I've highlighted here, and they account for very less, 14%, 13%, and less than 9% for as major issues for less than 9% and less than 15% of the people. This is a big leap from where we are. We still have memory issues somewhere out there, but it wouldn't be because of the safe code that you can write in C++. Okay, so these are the stats which I just summarized. So why don't the C++ developers have memory issues? And my question to you is, are you on that boat that you don't have the memory issues, or are you in the other ones where it's a serious concern for you? What really has changed? Let's find out, and let's learn on what we can do to save ourselves from falling into memory traps. That's me, architect at EXFO. So high performance telecommunication products is what I work on, making them cloud native, and love for the new and keeping up to date with this, with the happenings in the C++ community is something that really drives me. With me, let's look at what we can do for addressing memory issues, for not having them in the first place. Yes. So what are the memory issues? What are the memory issues? I'll just quickly show it to you. I think at least we appreciate what might these be, but just in case and just as a refresher. So you do a new, for an array of items, you got all the green items, and then you delete just a single item with the wrong delete, not a delete array, but with a delete in the first line. Or on the other hand, you just allocate one item and you delete an array when you actually delete. That's the incorrect delete. It might mess up the memory pool managed by the new and delete. Memory leak, you knew, but you never delete. Okay, there's a coloring issue there. It all stays green. So I guess, yeah, I'm showing you just one new. So you never delete it, and that piece of memory is never available again for you, although you don't need it. Double delete, so you already deleted it. You did a new, then you did a delete. Now it's red, which you released back, And then there are these gray cells, which I indicate in this as memory, otherwise just lying around. It's in the control of the memory management. But if you do a delete again on the red item, which is already deleted, you have a double delete, double free problem. Use after free, if you held on to the pointer after the delete, that's what this row shows. You did a new delete, it became red, but then you're still using it. That's a memory issue. It'll give you all kinds of segmentation faults, etc. Uninitialized use, you didn't allocate, you just have a pointer, you just forgot to allocate, and uninitialized, you started using. Out of bounds use, you allocated n items, but you ended up using n+1 or something beyond. Okay, so all of these are the kind of issues that we have to deal with. Now, if I give you this kind of a function, okay, an f which gives you a pointer, and I take it in p, can you tell me which of the lines on the right hand side, which I'll show you now, would be correct to write? And I can't, whoever can speak, you can speak, please. Value at p. Should you do that? Are you safe to do it? Maybe you are. Anybody? But maybe you're not, because the pointer can be null. You don't know for sure till you check. Can you increment to the next one? Not sure? Maybe you just got only a pointer that is just one object and not an array. Had you got an array, going to the next item, if it was within the bounds, would be good. But you don't know from this, you just can't say. Okay, and say for the first item, what if f was some find and it never found something? You cannot dereference it. What if this is returning just a single object? You can't go next. Again, this is accessing 5 slots ahead. Again, you never know whether it's there. Should you delete p? That should be right, correct? Or should this be the correct one? Again, you don't know. So there are, and should you even delete? Are you just looking at somebody else's pointer, somebody else's object, and that's not your pointer to delete or own and release? Nothing of that sort is evident here. And if you see the C API, you call strdup. To duplicate a string, you get back a string. But that you own, you ought to delete it. If you call str, which finds a string within your string, you get a pointer, but you're not supposed to delete it. Not at that point. The string that you own right from the beginning, that's the memory that you need to release. So the C API, which we inherited from from C, which C++ inherited, is giving us all these kinds of problems. Okay, so given another example, given a class C1 which has a const char pointer A, some x pointer B, some p pointer C, some const d pointer D, should the destructor actually do what? Delete A, B, C, D, or delete array? Which one is the array again? And just because it's a const, the char is const, the string that this points to is const, it may still be dynamically allocated. You are saying you don't want to change the value, but the pointer that you have, don't be misled by this. Const is for the character. The pointer is not a const, and you might still own the memory and may have dynamically allocated, and you need to release. And I've been unfair to you when I asked this question, because really, this is what a real class would be. The class C1, really, I just masked all the names. It would be an order. The const char pointer was a name. The x pointer was an items. And from the plural, you might be able to guess that it is holding more than one. Insurance policy, there's just one, it's a pointer, and a const agent is maybe the agent who sold and should be credited for this order. Okay, but so this order cannot own the agent, the employee of the place. So now the question is better qualified with the names and the types, but we really still don't know. Okay, I've described in the comments there. And you see policy here may be a shared ownership with a finance docket, it may be present there as well as in your order, and you might not be the only owners of it. And because of these pointers, all special member functions must handle these pointers. If you let the compiler write member-wise copy, member-wise assignment, you will mess up with memory. And that's why we all fondly use the term deep copy, because just copying the pointer is not going to help. Anyway, so from C++ inherited this way of having a reference semantics. For two people pointing to the same object is basically having a reference to the same. I'm not talking of the C++ reference particularly here, but in general terms, it's a way of pointing to the same thing. Passing pointers is efficient for non-trivial types. We want to be able to do that. We don't want to copy objects if they are big. But we have problems like, is it null or not? Can I be confident to use it? Creation with a garbage value, so you initialize it without any proper value. Ownership, do you own it? How many elements? And many pointers can point to the same address. So shared ownership of the same thing, that all seems like problem. And our endeavor, one-on-one on the right-hand side would be to be clear about the presence and absence of the value, to be sure that it is initialized, manage ownership in a managed way, handle ownership in a managed way, handle multiplicity, how many items there are, and shared instances. And this was a tweet I just came across yesterday, but very, very interesting. So C introduced raw pointers, and C++ is just trying to prevent people from using the raw pointers, just for fun. So we look at these member functions from that class who have to manage this memory. Okay, I'll remind you, we had this order object. Okay, and it had these items as members. Now, due to pointers, you need to explicitly initialize them. Although the default constructor can be created by the compiler, but it would not assign a proper value to them. So if you want them zeroed, either you say the member equal to 0 on the inside the class itself against the pointer, or you have to write this constructor, default constructor. Your assignment operator has to take care of these. I'll just show you one where I'm just showing the copy constructor here. So in the copy constructor, you need to delete the previous name and duplicate with a new name. That will give you a newly allocated name array or name bytes. And in the destructor, you have to delete all of them. And if you see, items are supposed to be many in an order, makes sense. So you have a destructor with array, deleter with array. Okay. So it's a lot of things that you need to manage manually, and you might go wrong. Okay. And what is the rule of 5? In C++ 11, we got move. And so everything else remaining the same on the left-hand side. Now, if we need to take care of move operations, where you move the implementation from one object to the other, you need to implement the move constructor here on the top right, which takes ownership of the other item which is passed to it, and make sure the memory is taken care of there. And the assignment operator is pretty much going to do the similar thing. So as you see there, you have to delete the contents of the other, because when it goes into destructor at the end of this function, it will try to delete whatever name it has, because it knows it has the ownership. We saw the destructor just on the previous screen, and it would delete this name. And that would result in a double delete, because now that same pointer is now here in our class now because of the swap. And this is clear recipe for disaster. So you have to null it and release it. Oh, I'm sorry, you should not have released it. We release our pointer. I'm sorry, this is a mistake. We release our existing name, whatever memory we are holding on to, and then take ownership of the other and make the other null. So assign null to the other and delete your own name, the older name. So sorry about this. I'll correct the slides. I hope that's clear. This is the rule of 5. The rule of three, which has been around since C++ 98, says that if you need to write a copy constructor, you pretty much also need to write the destructor to manage the same memory, because why are you manually writing that constructor? And you have to also take care of the copy assignment operator. These are the things on the left. In the rule of five, it became rule of five in C++ 11 because we got move, and you have to now take care of the move parts also. So you get the move constructor and the move operator also to take care of. Too much work, I would say. But any questions? I'm not looking at the chat or the questions, so you'll have to read it for me, please.
I am following those. There are no open questions at the moment and nothing in chat either. So attendees, if you have any questions, please feel free to use the Q&A bar to drop your questions. Ankur can answer them for you.
Yeah. Yeah, I like to take questions as we go. I'll pause to ask if there is a question. Okay. So the more code you write, the more possibility of errors. You should be able to do without writing code. How about that? Killing your own job. But it's a reason for error to creep in. When we see the character pointer name there on the left, definitely we know that there exists a better option. It's our favorite std string. Let's use std string and see what it changes for us on the same object. Okay. Clearly looks like a good strategy that you replace your char pointer with a std string. So your order now has a string name, not a char pointer. You don't have to initialize it in the constructor because the object will construct itself clear without any string value, no dangling things there. And if you see, we are just looking at the copy constructor, and the others will have to follow the same style. You just create it based on the right-hand side. That's the copy constructor that you have to write. The object knows how much to allocate, how to write the bytes. And as we all know, when it gets into the destructor, it destructs itself when it goes out of scope. This is the guarantee that C++ gives us on the closing brace or on the close of scope, that objects destructors will be called. And so will, if the orders destructor is called, so will the destructor of name be called automatically as a part of it. So you don't really have to do anything for managing and releasing memory for name. It's a string and it manages itself, right? We want to have subordinates and people working with us like that, right? And spouses and friends who do things you don't have to tell them a second time. Okay. And because we have move, we'll discuss the move operations. For move, this word move out, this can actually move out. So I'm sorry, this is also a typo. This is built just like the copy constructor. Here it should be name, and what you pass to name in the brackets would be move of the other dot name, so that has nothing now, and you place what you have in the other object. Steal the guts, take the memory, don't have to allocate anything. You just update your internal pointer in the string, your length int, and your capacity variable if there is more capacity than the length. That these things are always there. And with these three int and pointer assignments, they are so cheap. You have taken all the representation of that long string, which may be on the right-hand side. And when it destructs, it would be null anyway, because as I said, it should have been moved, and we have ownership of our new of the new memory from the right-hand side. And of course, the existing memory, when you call this constructor, any existing memory, in the case of the operator move operator, will be released. As a part of swap, you give your memory to the other, and other's memory you take. You just swap. So that at the end of that brace, when the other goes out of scope, it's an R value, it will be dropped, deleted, removed. It will definitely be released. Your memory, which you owned so far, will just go out. Okay, you don't have to do other dot. Again, this slide is a little apologetic. I'm apologetic for that. Sorry about that. Okay, so it's clear, right? The string eases everything. You didn't have to write anything, and it just works. And I want the same thing for all of my types. No management is the best management, right? Okay, income unique pointers, as you would have guessed. That's not a strike off. I tried to underline. So due to pointers, the order had an insurance pointer, which it was holding on to, but you had to do all the manual things. Similarly, for unique pointer, if we see, again, this time, even the policy doesn't need to be written here. Okay, and our copy constructor now can just give to the policy a new instance of the right hand side. So just for your information, unique pointers do not have copy enabled. They have their copy constructors and copy assignment operators deleted. You cannot copy. That's the whole idea of uniquely pointing to an object. You own it. Unique pointer in C++ represents ownership. So two people can't be owning the same memory. That's the whole root cause of the mess. So here we have to do something manually in order to create the new, if you wanted a copy. But by default, unique pointer will not let you go wrong. Okay, so if you if you gave the other dot policy into this policy, the compiler would definitely not allow that. Your code just wouldn't compile. And you have to do something manually there, like I have done. Create another unique, looking at the object inside the other dot get. Okay, other dot policy.
All right, Ankur, we have a question. If you'd like to take it. No?
I'll just finish this. The destructor, like string, we don't have any need of deleting the policy now. It's a managed object at its destructor. Its responsibility is to call the delete. And it's pretty much like the string. Yes, please. Sorry.
No issues. So the question is, why would we need to do an explicit move inside the move operation? The R value reference should behave just like the L value reference in the function.
Yes.
Please clarify.
Yes. So in this function, when you get other, okay, you used other dot name in that first line. Let me have the pointer. You have other dot name here. Okay, let's say this was taking the whole object of other. Okay. Okay, following. I'm not talking about name here. It's XYZ taking your other. And if it moved everything out of this other, what will the second line do? If it had to do something more with the other, then there is a body in which other is definitely a valid object. In Rust, you can't use this moved out object another time. Okay, but that's not the case in C++. We don't have destructive moves. When you move from an object, it goes into an otherwise unspecified but valid. I don't know about valid. So many operations are not usable, but it's a cleared out object. A moved out object is a cleared out object basically. Okay. So this is the example of the copy, but I was talking about move because of your question. I hope that's okay. You can follow it up with anything else. So because the next line can use the object again, and it is expected to have the value, you have to explicitly say that you want to move it out. So you have to write std move, because in the local scope, it is an L value. Okay, it has a type of R value. In the local scope, it has an L value. It is an L value. Because so this is a welcome guarantee which I just presented. That unique pointer will not allow you a copy. So two people cannot have the same pointer. Okay. Now this is the part where we look at the moved, the move semantics, the move constructor and move operator assignment. So you don't have to delete explicitly, obviously, but now you have to move the policy within this other object, and then you start owning all the details of that object, and that object is pretty much cleared, because the insurance policy would have implemented a move constructor itself. Okay, and it is just best to organize your code. That's the whole reason you have an object, because it should be able to manage. It's an independent manageable chunk of functionality. And what if somebody else, if the order class had to manage the internals of the arrays and the text inside this, or any other things inside this, what good is that class? A class should be open to extension, but close to modification. Basically, it should be a complete functionality, and others should not have to manage its internals. You should just talk at move it out, construct it, destruct it, use it kind of a level. Okay. Now, for array objects, you would create a move pointer like that with the array with the array subscript, and that tells the unique pointer that this is an array. Okay, and you allocate it just the same way, but this time you have a make unique with an is overloaded, and here you have to provide a size, and so it allocates that much memory, and the items is now formed. Okay, and now items also need not be managed, because at the end of this, a delete array would be called very correctly, because you said you have an array of items. And here you didn't, you just had one, so that would call a delete. Okay, so, and move constructor, move assignment, pretty similar. You just swap the two and let the other go out of scope. Okay, so all that array is now yours, and yours becomes the other objects array, and that goes out of scope and deletes. All right. So managing single and multiple objects, now we have this transformation. We started with the class on the left. Of course, it has string. So maybe I think I'm showing just last two steps here using the unique pointer here. And now we have managed object. Now this order pretty much we saw had nothing to do, but there was a detail which I actually skipped over, and I didn't let you catch it perhaps by going fast. Shared ownership was mentioned in my comments when I described the class. So it's about who goes last. So many people have shared ownership. Whoever goes last will get rid of the memory. Okay, let's see that. The insurance policy I told you was shared between this object and the finance docket object, which held all the policies that maybe the company would deal with. And so there's both are owning the policy. Maybe the finance department wants to discontinue it, or this order also wants to add things to it. So it is really a shared pointer. And this is where you now have an object really shared, but in a managed way between different owners. Okay, so this is like a ref counted. It is a ref counted pointer where a reference count is kept, and as many owners of the memory there are, the counter keeps on going up. The moment it hits 0, which means the last destructed, last shared pointer pointing to this memory is destructed, it will just go out. And so for shared pointer, all you have to do is nothing other than what you would do for a member-wise copy. You just pick the other policy and also become a shared owner of the same. And when that order goes away, maybe it would deduct its own shared counter, the shared ref count, and that's all behind the scenes. And you always do have a managed and a valid object. Till you let go of your reference, you have a valid object at all times. Okay, and so if we look at the shared part, we don't have to do anything special. It can be moved or it may not be moved. Okay, because it's a shared ownership, you would rather not move actually for a shared pointer. Okay, so with all this, the class looks like this now. All managed. And there was a trick which I played on you previously, which was here in the red text. I told you that items would be made and how many of them. I passed something called a size, which was really not there in the, sorry about the animation, really not there in the scope of this function. Where does this size come from? Now, as you know, as we discussed at the first in the first half of this talk also, that pointers don't know how many items there are. Arrays decay into pointers, and pointers don't know how many there are. You don't know if you can go plus plus. So there is no way to find out what the size of the array was or would be. This is not the unique pointer's job. Unique pointer's job is to manage its memory, and that's it. If you want to manage the size also somewhere, you need to know it. And so how do you manage many items? You use your trusted vector. It is, of course, a managed resource. So you just, in your copy constructor, take the items from the other item, from the other dot items, and you have your own copy of the items. That's the copy constructor. And of course, you have to do nothing in the destructor or in the assignment. If you didn't write it for a vector, assignment, move, all these are defined. And so you can just use them. And so here we have the vector of, that's a copy slide. Okay, yeah, I wanted to show vector here. So this is a vector of items, and for move, all you have to do is to std move the other policy into this policy. Similarly here, std move this policy into the other policy. Okay, so nothing to do in these special functions now. This was the class that we had so far. They were only the members. And now we really don't have anything to write in the order class for the special functions. You will still have your business functionality written somewhere or in some other members. But all this management business, you don't have to do any of that. Just because you have, excuse me, you have in the order only objects which are themselves fully managing things. This is the RAII idiom that we have in C++. Okay, you better use your time to focus on your business logic than on writing all this code. The compiler will generate a member by member, copy, move, destructor, and you don't have to do anything like that yourself by hand. Any questions?
Nothing in chat at the moment.
Okay, yeah, let me know, interrupt or something. So we now have so the other aspect is a discussion about the nullability of pointers. Now pointers can be null. Okay, that's an inherent quality of the pointer. So when you have a function like this, order.setAgent A, should you have to check that A is the null pointer or not? If we all had to write this code and every pointer you pass, and I've seen such code, every parameter has to be checked. If you didn't give the things that this function needs to work on, what else are you calling this function for? This is a paranoia I've seen in many people that, it's fair enough to check, but you might do without the check. And most probably you cannot do the right functionality without the item passed correctly. So at this point, I would say you should use a reference or and not a pointer. Okay, if it's something that you can afford that it does not change, it can be a reference and not a pointer. For function parameters, I would, which is what this item is about, by passing, I mean function parameters, you should, if you use a reference, the responsibility onus is on the caller and you don't have to do memory management. Or check for the null pointer, or confuse the semantics. Now, do you own this memory or not? Okay. And for surety, I would say you should not hold on to somebody else's pointer unless it is assured that it is, it is still going to be alive for the time period that your pointer is holding on to that memory. And if it is not easy to prove, use other constructs. Okay, don't use a pointer, use a reference if it must be something. If there is a possibility that you have null, sometimes you don't have the item, or maybe it is something that will come later, then you should work with values. Think about that. We'll cover some of that later. Foolproof management. Further, the use of these pointers also help you address leak. Consider this code where a create server factory function is trying to create a server. It has a new server. It picks up config.json and loads it. If that failed, okay, sorry, I did not show you the error, but I was only semantically conveying my meaning here. If that return an error, you just go back. You just have nothing else to do because you can't proceed. It's fatal for this logic to continue. If you connect to the other party and you want to throw a connection error, you subscribe to something after connection, but you run into an error and you just can't use it, can't do much with it because it's not much use without the subscription, etc. maybe. And you create a fully created object and then you send it to the user. This is pretty much that function F which we saw at the beginning of this presentation, where you really don't know what to do. We know from inside that the ownership is given, but the biggest problem here is early returns or the exceptions which can happen, which would leak this resource right here on the first line. And if you just used a unique pointer there, you don't have to manually worry about cleaning up. Okay, so no raw pointers as shown parent in the signature talk. This is a picture from the seasoning talk, C++ seasoning from 2013. No raw pointers that own memory. Use pointers to pass on objects for temporary usage in the functions. And the CPP core guidelines has many such things of suggestions of using pointers. If you have to use them and for efficiency purposes, you should use them, but within the realms of those of the guidelines. Okay. So by default, at least ownership node should not be implied and leaking, etc. So all that just goes away if you have managed things. Okay, what are some of the other managed types? This, I guess you would have guessed if from the title of my talk, what I might be talking about. But there are so many other managed things. We already looked at vector. Just like vector, we have std array, which takes a type t and a size n. And like an array, the size of this, like a regular, what do you say? Like a array in C, this std array is definitely decided. The size of its of the number of items in it is decided right at the beginning at instantiation, and it stays just that much. And this now is just like any other container. You can iterate over it. It has iterators. It has the type defs and the using the value type, etc. in it. It has it can do all that the other containers can do. You can replace the items as I'm doing here. So yeah, it is fixed size and managed, and it can be instantiated and then initialized. So you just use it just like an array. But this array never forgets the size. Here, if you do array.size, like we were able to do vector.size, you will always get what the size of this array is. So you can pass around this array. You can like a vector, you can use these this array to contain many other things, but this will be a fixed size one. So go for it if it serves your example, serves your use. Okay. STD variant. Variant is a type safe union. In C, we had union. We had to use the memory in the same set of memory by saving memory. By having many kinds of objects in the same memory location, we saved some memory, and we were smart with things, but not so much, because if that had some allocation, etc., the type safety is a question. One of the questions that we other time in the other place in the survey also we saw was type safety. And being in C++, we should strive for more type safety. So let's consider these two kinds of structs or data types present. They actually are a part of let's say, a state machine. Your state is either connected or state is disconnected. But here, the state is not an enum, state is a struct, because at a certain state, you have some members. In some other state, you have some other members. If you had a God object of state, which had all these kinds of members in it, and you have to remember and use the right member of when a timer is valid only in connected state, when the last connected time is valid only when you are already disconnected, this would make your code clumsy and error prone. So how to use memory use items in a type safe manner? So here you should have a variant which could accept any of these two types, and like a union, it would hold on to the types. It would just have enough memory to hold on both kind of types, and it could start with any of the types. Like here, you could just assign it like you assign two objects of connected to each other. And it would take care in a type safe way that the previous object, if a disconnected object was present in the variant and you now assigned a connected object, the disconnected object would be destructed properly. Okay, again, it's exactly what you want. No leak, no issues with any other resources, not only memory, but any other resources like connections or identities that you hold on to. Okay, and now you can refresh this timer. So here, after you have the connection state, it isn't connected. Once you know it is in that state, you can just use the timer inside it. And the way to use it would be by a visit. I think I have the last line on this slide. Later on, you disconnect and your state changes to disconnected. You assign the disconnected object, and properly the connected object would be deleted, would be destroyed. Sorry, not deleted. And now the last connected field is there. Okay, so you don't have to clutter all the logic with the kind of things that with the kind of possibilities of when some members are valid and when they are not. You can have a type safe memory use here, and you have to use visit. So if both connected and disconnected can be used the same way, here we are doing a cout we are just printing what it is. This one lambda could just serve both the types if it's the same interface. If you want to, there are ways to handle two different types slightly differently or totally differently if you want. So there's a way to visit and handle the two types differently in this lambda. And all you say is visit with this lambda, this variant of mine. Okay, so the correct type value, which the variant always knows, will be picked and sent here. There are many such objects here. If you see iStream, IFStream, these are all also resource managed objects. Okay, they take care of their own things. If you create a copy of FStream, the new file will not have the offset and pointers where the previous one had, but it will be able to. It would have in a managed way, in an organized way. It would take the guts out. If it was a move, it would copy. If it was a copy from one FStream to the other. So there are many such objects, and our endeavor should be to write business objects of that kinds, which are managed, which are managing their own things. Okay. Any questions at this point?
I don't see any questions, but as a time check, there are 10 minutes left
10
for our
minutes.
talk. So if you've
Thank
got
you.
any questions, this would be a good time.
Yeah. Okay, return value optimization. Let's see what this is. C++17 brought to us guaranteed return value optimization. Compilers were able to do it before. Let's see what we did before. If you have this kind of a factory function, and if you created a connection object, and I'm assuming this connection object is expensive to copy, etc., you would be worried at this line in C++98. Is this doing a copy? Will my objects be correct at this point? Is it fair? Is it right to copy? And you get into the realm of having to define all those copy constructors, etc., or pay the performance penalty that you are having a copy. And if you instead have a pointer, this would be the motivation for a pointer for many people. The fact that you don't want a copy, you create a pointer and it's allocated on the heap inside this createCon, and you just return the pointer. What a relief, right? Now you have pointer, and again you're back in that same land. Okay, of course you could make it a unique pointer, but consider that the first line lets you write this, and to circumvent the pointer and having to manage the pointer, you could write something like this. You create a connection object, and then you create and then you populate it fully. Okay, this gives you the typical not so good to have instantiation and initialization separation. Instantiation is happening here, but it's not a good object, not good enough to use, and initialization is happening here inside this function. And you know what, you yourself tomorrow, forgetting this part, might write something like this here. Okay, and now you have used an object which is not fully initialized or not ready. And this is, so avoiding this pointer is something you can avoid. This out parameter is something you can avoid, because now in C++17, if you create a new object inside this function and return it and take it into a connection object in your frame, you are guaranteed that this will result in no copy, no move. The object inside that function is really created at this location or in your local variable, in your member variable directly. So you don't have to deal with the pointers, or you don't have to deal with this kind of passing out parameters, etc. And no copy is guaranteed, right? And we can stay in object land. So what it allowed us to do is, even for a huge object like connection, even for a huge object like server, you can actually return by value and be sure that you have zero penalty, and you have object semantics controlled by the braces, no possibility of leak, etc., and all that. Zero overhead truly is what C++ is known for. Yeah, clear? I'm going ahead, just let me know. std move then. Now move, with the return value optimization, move can do some magic, and having move semantics was a boon in C++11. And why I say that is it makes moving things around very inexpensive. Previously, just if you see that previous example, or I've written a new one here, if you had something like this, a user's cache, which is a huge vector, and it has very cache is a very happening place, things coming in and out, and you keep on using it. Now the user changed some things, and you need to do a lot of copying, etc. So traditionally, if the return value was not guaranteed, this is not a return value thing, because had this been a constructor, the return value has guaranteed and eliminated any problem there. You can directly work with the objects, right? But this one is about move. So if this is giving you an object back in your C++98 world, you would be worried that all the items in this would be destroyed. All the T's inside this would be destroyed. The memory will be released, and then new memory will be allocated based on what the vector that you passed here. All the items would be copy constructed in place in this new memory that you created here. And if this was returning the vector, of course, that vector will go out of scope and delete the original items which this function had created. But with move, you just copy the pointer a size, a capacity item, some 3 bytes, sorry, 3 int wide items from the right hand side, from this R value, which is what a return temporarily returned object is. If you just pick it from there, these 3 item copies, which is what the move gives you, just helped you not have to pay any more penalty than you must. You just have to free the other memory that you had. Those users are going and new users are now loaded. And so with a little cost of just swapping some pointers and integers, life is ooh la la. RVO and STD move really work the magic. Okay. To add to it, we have STD optional. STD optional is another managed object where this object can optionally have a T or not have anything. This was introduced in C++17 also. So if you have a case where you get something or you don't, now you can use STD optional. So if you were finding an employee and you return an employee, you could, maybe find is not a good example, but if you're working on an object and you want to pass the object back, which previously you had to use pointers in order to save the copy, etc., and you still want to have the possibility of not having the object because something went wrong, an exception was thrown, you had to come down to pointers. But now you don't have to use pointers. You can use STD optional of T, and it may or may not have the value. This object allows you to query whether it has a value or not. It's a bool, it's convertible to bool. If you just write if this object, it tells you yes or no, it has a value or not. If you check the has value, it tells you the same. With the function called as value, you can pick the value. Okay, and you can even move it out of this optional and take it in your object. So with that little move, you can start returning optional from your functions. So this is an example. Find employee. I wonder if employee by finding would be returned by, a reference could be returned. But if you had a reference, you could not send back the case where no employee was found with that name. Okay. So it's always possible in a find that you don't find something. So so this is how you do it. You take the optional as a return type. Find employee has an optional employee reference as the return. Even with a reference, it is optional. It may not have a value, but if it has, you can go ahead and use it the same way. Okay, and its dot value would be implicitly called and passed to this use function. And the use function is just taking a regular employee reference. Okay, like it is shown here. Here, when you use, let's say the use returns an address. Okay, the optional that we saw on the previous screen also has some monadic interfaces, which have been introduced in C++23 now. More reason to upgrade your compiler and C++ standard, the standard version. This allows you to chain operations. So I'll just show you by example what it allows you to do. So find employee dot and then use, and you pass the use function to it, and it would then call the use if this optional returned by the find employee had a value. If it didn't have a value, it would just return and stop the chain. But if you had this chain where use is giving you the address and you want to print the address, you can chain your operations like this. Such a good functionality to have. And so even if you had a pointer, don't get into the realm of having null pointers. Why not use STD optional, which will just hold, STD optional will not have any additional overhead, I guess. It has the overhead. It possibly has an overhead of a bool beyond the pointer itself, but it's so small that you should not have to worry about it in modern systems. And it really being all, if you work on it only in the value land, obviously that is the whole idea. You take the optional, all of these may just be worked out in the register itself. You may not even go to an address space and allocate memory for it. Okay, so it's impossible to use a null pointer if it was not checked and all that with this and then. And you're very sure that everything is going to be right. Previously, in June, I had made this presentation where we looked at this kind of a sequential thing, and I've seen this very often. From an environment, you pick the file contents and make a client, apply config, connect, subscribe. So this is a very much a kind of a value-oriented implementation.
Time check, Ankur. We're at the top of the hour.
Yeah, and I'm on the conclusion slide. Half a minute. So do not manually invoke raw memory management primitives. Don't do new and delete yourself. Use pointers. Pointers do not own memory. Let pointers not own memory. Use the types that manage themselves and uphold your values high. You are in C++. Now that you have the better tools, why don't you use them? These are the ones to use and save yourself from all that pain or having to GDB. Much less effort than learning a new language for sure if you just learn the new ones, and all your product still continues to work in the same language, and you just add more value to it by creating new functionality and selling it. Uphold your high values. No room for raw pointers here and manual memory management. Thank you.
All right, thanks for that talk, Ankur. We have one question in chat that I think you should take before we close it out. So from Honey, she asks, is that RVO guaranteed only from C++ 17? Move semantics was introduced from C++ 11, right?
Yes, guaranteed from C++ 17, although even before 11, move was being elided. RVO was in play. I've tried that myself, and I didn't know why the vectors constructor or destructor, or why my objects destructor, constructor, or copy constructor was not invoked even before 11.